Yes. Is it recording?
Okay, so first I would like to thank you for the invitation to give this talk, and I would like to apologize for not being able to be in presence with you in London. The reason is that I have lots of other applications here in Munich in this week. We are in the middle of the teaching period, and I'm just unable to travel in the middle of this period. My apologies for that. I would like to tell you something about a model for dislocation lines in three-dimensional solids at low temperature. And what I'm going to tell you is joint work with Roland Bauerschmidt, Diana Konaki, Markus Heidenreich, and Silke Rollis. We did this work approximately 3 years ago. Unfortunately, I have nothing newer to present, but only open questions that are unsolved at this moment. Well, it's a first step I would like to tell you. Let me start with some motivation. Let's look at a crystal at positive temperature. It may have dislocation lines. I should mention that I have not drawn this picture. You can see, I hope you can see it. Can you?
Yes, yes.
Okay, fine. I've not drawn it myself since I'm not such a good drawer. I've taken it from Wikimedia. You can find the link here where it's from. So you can see here a crystal, but at this location here, and this location over there are two dislocation lines, and here's the third one. So here the crystal structure is perturbed, and you can well imagine that these dislocation lines in 3 dimensions cannot be localized. They are lines that cannot be localized just at a single point defect, as it could be in 2 dimensions. So how do we describe these dislocation lines? They are described in terms of Burgers vectors. Let me introduce what these Burgers vectors are, also using this figure from Wikimedia. I've not drawn it myself. First in 2 dimensions, because in 2 dimensions it's simpler. Let's look at this defect in our lattice, or maybe I should draw it here. You can see it even by not only looking at the location where the defect is, but going around a curve around it. So when you start, say, at the point Q here at the bottom, and then you go 1, 2, 3, 4 steps to the right, and then 1, 2, 3 steps upward, and then not 4, but 5 steps to the left, and then 3 downwards, you get a closed curve. So you see, it's not like an ordinary lattice when where you have to do equally many steps to the left and to the right as you do steps to the upwards and downwards in order to have a closed curve. So this is a characteristic for the presence of such a dislocation line. You can see it even away from the location of the dislocation line by looking at curves surrounding the dislocation. The same is true here in 3 dimensions. Let's look at this picture. Here, let's start at this point O. Let's go 1, 2, 3, 4, 5 steps to the right, then 1, 2, 3, 4 steps upwards. Then 1, 2 steps to the left, but 1 step out in the 3rd dimension out of the picture, and then again 1, 2, 3 steps to the left, and then 4 steps downwards. And you see we have a balance of this extra step out of the picture in orthogonal to. So this this curve is associated to a Burgers vector pointing outwards of the picture. Now, in order not to describe the precise microscopic structure of our crystal, in the model we use, we look at a continuum description of Burgers vector, not looking at individual dislocation lines, but a continuum description of these dislocation lines. So we describe the Burgers vector by a Burgers vector density, which is a tensor field, B like Burgers, and I, J, and K are directions 1, 2, or 3 in three-dimensional space, where the first two components, the I and the J, describe the directions that we use for our closed curve, say a parallelogram going around a region in space. So, for example, here in this picture, I is the index for this direction. For example, it could be I equals 1, and J is for the second direction. So here I equals 1, it's in X direction, and J equals 2, it's in Y direction. And here again, this is X direction, I equals 1, J equals 2, and then when we look at the direction coming out of the space, K in this case equals 3. So there's Bijk component for 1, 2, 3 in this case would be non-zero. So K is then the component for the Burgers vector we look at. Okay, actually we do not analyze a realistic crystal, but just a toy model. It's simplified in several respects I'm going to mention. It's only a toy model. It's three-dimensional, but it's not on the atomic scale, but it's intended to describe the mesoscopic scale. So a scale where you can see still the effects of dislocation lines, but still a scale which is small compared to the macroscopic scale. So in atomic dimensions, when you think of the atomic dimension being something like 10 to the minus 10 meters, and the macroscopic scale being something like 10 centimeters, and it could be something like a micrometer, something in between. That's so you cannot see individual dislocation lines, but you can still see the effects of them by deforming the crystal. Okay, so we analyze this using equilibrium statistical mechanics. So there's no dynamics. And one motivation was for us, and also some of the ideas that we try to mimic in our model are taken from the analysis of the Villeneuve model by Fröhlich and Spencer something like 30 years ago. So that's somehow some ideas of the analysis are taken from there, but in a different model, in the Villeneuve model, which is a scalar model rather than our vector valued model here. Now, what is the goal of our work? So the goal is to understand how it comes that rotational symmetry is spontaneously broken. In fact, we are not looking at the full rotational symmetry, but in a linearized version. But the guiding problem behind it is to understand why is it that dislocation lines on very large scale in thermal equilibrium do not perturb the long-range order of a crystal. Why is it that the dislocation lines in a thermal equilibrium on very large scales are not so much visible anymore, such that they could destroy completely long-range order. So the work I'm going to tell you about is in this paper. Dislocation lines in three-dimensional solids at low temperature. It's just the same title as for my talk. As I mentioned, it's joint work with Roland, with Diana, with Markus, and with Silke. But there's also recent related work by Alessandro Giuliani and Florian Theil, which is in a different model, but on an atomistic scale. So long-range order in atomistic models for solids. I'm going to mention a little bit more about it in a few minutes. Okay, now before I start to define the model formally, let me describe what its basic features are. As I mentioned, it's a model in equilibrium statistical mechanics. There's no dynamics and there's no non-equilibrium in the model. Of course, real solids hardly ever are in complete thermal equilibrium, so it's a very idealistic model, if you like. We look at it at small temperature, but not at temperature zero, so there are thermal fluctuations. We look at it at positive but small temperature. And as I mentioned before, it's a model intended to describe a mesoscopic scale. So there are no atoms modeled in this description, no individual atoms, but the local displacement is modeled by a smooth field. And then, at least for the elastic deformations of the crystal, we use linear elasticity theory. So we use a quadratic form to describe elastic deformation. So linear elasticity theory is used for the elastic energy. And then there is a simplifying assumption, which is not essential, but it just makes things easier to write down. We use for the quadratic elastic energy an isotropy assumption, which is fulfilled in FCC or BCC or phase center cubic or base centered cubic models, or simple cubic models as well, but in many other crystals it's not simplified. But this is not essential, it's the easiest case to write down. But one could do the same theory even without this isotropy assumption. It's not actually essential for doing the analysis. Now, here comes another simplification. In order to reduce the complexity of possible dislocation lines, we use a small distance or an ultraviolet cutoff. So dislocation lines are only allowed to be supported on the edges of a mesoscopic lattice, which should not be confused with the atomic lattice. The atomic lattice actually is not modeled at all, but just in order to reduce the complexity of possible dislocation lines, the combinatorial complexity, we allow dislocation lines only on the edges of a mesoscopic lattice, which with an edge set, which is denoted by lambda. The vertex set is denoted by V lambda. And once again, it should not be confused with the atomic lattice. But in order to make, in order to avoid singularities at the location of these edges, we smear these edges out with a form function phi with a small support. But the Berger vectors themselves do not take values in this mesoscopic lattice, but in a microscopic lattice, lambda. Just maybe I'll show you once again. So here in this example here, the Burgers vector is on the scale of the atomic lattice itself, even if a curve surrounding it might be on a very different scale, length scale. So this lattice lambda, where the Burgers vector takes values, should not confused with the mesoscopic lattice, where the location of the dislocation lines is assumed to be in this model. And the goal of the whole theory is to show that in this model, linearized rotational symmetry gets spontaneously broken. Okay, after mentioning the main features of the model, let me come to the introduction of the basic objects in the model. So first, we describe the orientation of the crystal in linearized theory by a field W, which is 3 by 3 matrix valued. So in the absence of the dislocations, you could think of W as just the gradient of the displacement fields. So the displacement fields assigns to any location of the unperturbed lattice, the location where it's after some perturbation. But of course, in the presence of dislocation lines, there is no displacement field because we cannot index in a natural way the locations of our atoms in the crystal in the presence of dislocation. So rather we use, so you can think of a local orientation of our lattice, more precise is a deviation of it from the identity matrix, which is 3 by 3 matrix. So it describes the local orientation of our crystals, at least in linearized approximation, close to the identity matrix. And then the Burgers vector density is just the curl of this field with respect to the first of the matrix indices. So our Burgers vector density I mentioned before is the curl, so it's the partial derivative in ith direction of the jth component of W with the kth component of the Burgers vector as the third index. So the curl is taken in the second index, but not in the third index. And for the curl, I write using this exterior derivative notation. The curl is the first exterior derivative, so I write d1 of W. So this d1 refers to the second index of W, while the third index, which gives you the component of the Burgers vector, is just added as an index. You can, if you like, write here times identity in the third tensor, the identity in the third component, but I don't write that. Okay, now for a model in thermal equilibrium, we need an assumption for the total energy. And let us assume that the total energy consists of a local part and of a local part for the dislocation. Let me go back to this picture in order to motivate this assumption. So here at the location of the dislocation, of course, it costs some local energy to remove or to add atoms or to have them in non-standard distances from each other. This is a local energy, and this modeled by a part of the Hamiltonian, which is not described by linear elasticity. It's far from a linear perturbation, a small perturbation of the crystal. So this is a local part in the energy. So here's it. It depends on the Wilkes vector density, and I call this H dislocation, the local part. But then, let me go back to this picture. As you can see here, even far from the dislocation, our crystal is not consisting of standard cubes, but those cubes are a little bit perturbed. You see these lines here are not straight lines. It's a little bit distorted. And for that, we use, away from the Burgers, away from the dislocations line, we use linear elasticity. So it's described as an elastic part, H elastic, so elastic part of the Hamiltonian, depending on W. And well, this local part, I use some symmetry assumptions that it does not change when you just use dislocation lines with Burgers vectors in the opposite direction. So in this, again, in this model, when you perturb your crystal rather than what is done here, moving the left part out of the picture and the part to the right inside the picture, when you revert the directions, it should cost the same energy for dislocation. That's this assumption. And another thing, the cost of the dislocation should be bounded below at least by the one norm of the Burgers vector density times a constant. And another locality assumption, as I mentioned, this dislocation part should be a local thing. When you have two Burgers vector densities with disjoint support, then the local parts of the dislocation energy is just additive. So when you have both of them, the local part of the dislocation energy is of the first, and the second is the local part of the dislocation energy of the joint thing. Of course, this is not true for the elastic part, but this is only about the local part of the dislocation here. Okay. Now let me describe these dislocation lines as I roughly mentioned before, but now in a more formal language. Look at a finite subset of our mesoscopic lattice describing the possible position of dislocation lines. And as I mentioned before, the set of vertices is denoted by V. And we give every edge bookkeeping counting direction. So this counting direction has no physical meaning. It's only used for bookkeeping purposes. So we can encode these things by a signed incidence matrix, which assigns to every vertex and every edge. Well, there's three cases. First, the edge might be an outgoing edge from our vertex. Then we assign to it a minus sign, a -1. So here we have a minus sign. When it's an ingoing edge to the vertex, we take a plus sign. And if the edge is neither ingoing nor outgoing to the vertex, we assign a 0. So this is a signed incidence matrix. And then our Burgers vector field is modeled by a function which assigns to every edge in the mesoscopic lattice a Burgers vector taking values in some microscopic lattice. But with a constraint that for every edge in the mesoscopic lattice, like this. And for every component of the Bürger's vector, the balance of these components for all edges is 0. So this reflects that these dislocations lines cannot stop at a point because it's coming from a curl, and the divergence of a curl is always 0. So in our discrete description, this is something like the divergence of a curl field is always 0. Okay, now this is just a discrete function, but you can think of it as a vector valued current. Think of it like an electric current, but with 3 vector components, this Bürger's vector field. So when you have an ingoing current here of, say, component 1, 2, or 3 of your current outgoing here, then you can think of on this line here, you have a Dirac delta-like current flowing in this direction, and then it splits maybe in 2 pieces, one piece here, one piece here. So it's a vector valued measure on these lines in space. So formally, we describe it by this vector valued measure Jk, which takes, well, the direction in which the Bürger's vector looks to, the direction in which the edge goes in its counting direction, and then lambda e is just the one-dimensional Lebesgue measure on this line. But in order not to have singularities at these dislocation lines, we smooth the thing out with a form function. So this form function in 1 dimension, you should think of just a little bump having integral 1. So it's just a smoothing function. So phi times convoluted with the JLK, and then with this totally antisymmetric tensor epsilon IJL contracted with this gives our Bürger's vector density. So that's a model for the discrete dislocation lines. Now, let me talk about the model for the elastic energy. So it's just the usual elastic energy for deformations of in linear approximation of a crystal. So we take this thing here for matrix U, 3 by 3 matrix, f of u is lambda divided by 2, the trace of u squared, plus mu times the 2 norm of u squared. So these constants over here are just called Lamy constants in material science. And then, as in linear elasticity theory in material science, the elastic energy is modeled by this f of the symmetric part of our linearized orientation field of the crystal. So it's insensitive to the antisymmetric part, which means that linearized rotations are not seen by the elastic energy. So this is quite standard in elasticity, in linearized elasticity theory. So it's just a standard elastic energy for an isotropic crystal in linear elasticity. Okay, and now think of we do a minimization of the elastic degrees of freedom. So think of a configuration with a given Burgers vector field, B of I, and think of all possible configurations which have this Burgers vector field B of I. So we look at all matrix valued functions, say compactly supported smooth ones, such that the kernel is our given Burgers vector field. And the infimum over all elastic energies with this given Burgers vector field, this I call the elastic energy of this, Burgers vector field encoded by I. And this elastic energy, together with this local dislocation energy I mentioned before, gives then the Hamiltonian, the total Hamiltonian, which is used for defining the Boltzmann-Gibbs weights in our statistical mechanics model. So given an inverse temperature beta, beta is 1 over temperature, or if you like, you can put here Boltzmann's constant, which you can think of being 1 in our reference units. So beta is 1 over the temperature. So because temperature is low, you should think of beta being large. The partition sum is just given by the sum over all Boltzmann-Gibbs weights of corresponding to all possible configurations of dislocations lines. And then the terminal distribution, so it's a measure on possible dislocation configurations. So the weight, so delta I is the Dirac measure. At I with a probability proportional to this Boltzmann-Gibbs weight, as a normalizing constant being this partition sum over there. So it's a statistical mechanics model with this energy on dislocation line configurations on a mesoscopic lattice as an input. Okay, but let me mention that there are null directions in this energy functional corresponding to rotational symmetry of the model. So when you add to W a linearized rotation, which is described by an antisymmetric matrix, a constant antisymmetric matrix, which you should think of a rotation matrix minus identity close to the identity. When you add this to the Hamiltonian, I mean, you add it to the argument of the Hamiltonian, so meaning you rotate at least in a linearized approximation your whole crystal, the elastic energy doesn't see that. Of course, that's a physical feature of the model, because the energy of the crystal should not be sensitive to a rotation of the whole crystal. And the same is true here for the Burgers vector density. Also in linearized rotations, the Burgers vector density does not see this linearized rotation. But this linearized rotational symmetry is broken here in the model. It's manifestly broken because we have this constraint that we are looking only at W's with constant, with compact support, meaning that whenever you perturb it by a constant matrix, the W, it will not have compact support anymore unless W constant is equal to 0. So this boundary condition breaks this linearized rotational symmetry. So you don't see these null directions in the model anymore by the boundary conditions for our crystal. Okay, let me first mention that there's actually a minimizer of the elastic energy. So for any Wilkes vector configuration denoted by I, there is a smooth function which is square integrable. Let's call it W star. So it's a dot argument stands for the R3 argument here. So I is the input I over here. With a following, so it's square integrable, but in general not with compact support, such that for any sequence Wn, which has Wilkes vector density given by the I, so the B of I associated to I, but has compact support, smooth with compact support, and with the property that the elastic energy of these along this sequence converges to the minimum or infimum of elastic energies you have for this Wilkes vector configuration, then you have convergence of the W's to along the sequence to this minimizer. So in this sense, there's a minimizer, although the W star itself is not of compact support anymore, but we can approximate it by functions with compact support such that it's in the L2 sense, such that the energy goes to the minimum energy. Okay, now let me now come to the main result of our investigation. The first thing is a property of this minimizer. So uniformly in the directions I and j being going from 1 to 3, so brackets 3 stands for the set 1, 2, 3. So uniformly in the direction you look at, uniformly in the location of 2 points in space, uniformly in x and y, the Fourier transform of the local orientation at x given by, for the minimizer wij star of x with a configuration I minus the corresponding quantity at y, and the Fourier transform of that, meaning we take the expectation in thermal equilibrium of e to the I, and then the difference of these matrix components of W star at I at x and at j, and uniformly in the finite set, the Wilkes vectors can have the support in. We have a Gaussian lower bound. So it's bounded by an exponential of minus t squared over 2 times e to the minus c1 beta, where c1 is a constant depending only on the input parameters of the model, but not on beta. And this holds for all small, sufficiently small temperature, or in other words, for all large beta. Well, maybe more intuitive is the following, which is just a corollary of it. So you can view this as a kind of infrared bound. Okay, so something about long-range order. So here's something which is maybe more intuitive to read, but actually it's just a consequence of this statement of the theorem. when you look at the matrix entry indexed by I and J are just numbers from 1 to 3 of the orientation of your crystal, of course linearized at the location X and the location Y for the minimizer, so W star. And you take the thermal fluctuation of it. So the variance of this difference with respect to the thermal measure. Then uniformly in the indices you take, uniformly in the locations of space, and uniformly in the box, or in the finite subsets more precisely, where your Wilkes vector may have support. This is bounded by something which is very small as beta gets large. So again, the same constant, e to the minus this constant times beta. So this gets arbitrarily small if beta is large. So uniformly in more or less everything in the size of the box you're looking at, in uniformly in the locations you're looking at, and uniformly in the directions you are looking at. So this is a more intuitive statement of long-range order. We can interpret it as follows. Linearized rotational symmetry is by the boundary conditions, at least at small temperature, spontaneously broken in the thermodynamic limit, even in the presence of dislocation lines. The thermodynamic limit means that you can take the box here where you have your dislocation lines as large as you want. Okay, let me use the last something like 18 minutes, or should I leave time for discussion at the very end? How many minutes should I take?
Maybe 15 minutes?
15 minutes?
Yes.
Okay, thank you. That's fine. So the first step is this minimization of the elastic part of the energy. This is done in a suitable Sobolev space. But some more interesting parts then are, and these actually were motivated by this analysis by Fröhlich and Spencer of the Wheeler model. So next step is a Sine-Gordon transformation, which introduces an auxiliary Gaussian field in order to describe the elastic energy, which is a quadratic form, by linear forms. I'm coming to that. And the next step then is to do a cluster expansion of the free energy in connected components of the supports of the dislocation lines. And finally, this last step of the analysis is to bound the decay of the observables, the W star of xi, using an ingredient of which is well known in magnetostatics, which is a deep dipole expansion. So somehow the dislocations, elastic dislocations behave like dipoles in magnetostatics. At least mathematically, it's very similar. And I would like to at least sketch these steps, or some main parts of these steps, in some remainder of the talk. So first, let me come to the minimizing of the elastic energy. The elastic energy is a quadratic form. It's a second order, it comes from a second order Taylor expansion of the elastic energy. Let me look at it again. So here, this is quadratic in U, and then so W plus W transpose is linear, so this is a quadratic form. Quadratic elastic energy. This quadratic elastic energy corresponds to a bilinear form. And this bilinear form I denote by brackets with index f. So if we do it over the complex numbers, which is convenient for doing Fourier analysis, we take it only sesquilinear, but not bilinear. With the reals, it would be bilinear. And then the kernel of the curl operator is a range of the gradient operator, or in exterior derivative notation, the kernel of D1, the curl operator, is a range of D0. This is true in an appropriate Sobolev space. So D0 is just the gradient operator. And now let me denote by nabla f. So f corresponds to we use this quadratic form rather than the ordinary or Euclidean scalar product. The adjoint of the gradient operator, but with respect to this sesquilinear form. So in formulas, it means that D0f, the inner product with respect to this sesquilinear form with any g is equal to this nabla f of g, this adjoint with f for all f and g in our Sobolev space. And then we do the following. Given our Burgers vector density, we first look at a W which fulfills that its curl is a given Burgers vector density, but is not yet a minimizer. So here's something which fulfills that. Laplace inverse, this is just the ordinary Laplace operator, also minus Laplace inverse, or Green's function, you could say, D1 adjoint B has this property that it gives you a WB which has a given Burgers vector density, but is not yet the minimizer. But then you get the minimizer somehow by projecting, using an orthogonal projection in an appropriate Hilbert space. And here is what the result is. You modify your W star by a gradient of a function psi star. Here it's explicitly written down. And then the claim is that this W star is our minimizer in L2 for the elastic energy. So the inner product of this W star with itself is the elastic part of the energy of I. So we now have an explicit description of this elastic part of the energy. Now, the second part, which I find a very interesting idea, which I learned from Fröhlich and Spencer, and we adapted it to our present situation. So, as I mentioned, the elastic energy is a quadratic form. Well, a quadratic form, the exponential of it, when it's positive definite, e to the minus beta, our quadratic form, is a Gaussian. And a Gaussian is a Fourier transform of a Gaussian vector. So we take appropriate center Gaussian variable on an auxiliary probability space, which we denote by phi, such that the Fourier transform of phi equals the Boltzmann weight of our elastic part of the energy. So e to the minus b, the h elastic minimizer of I. So this is a funny idea, because inside this expectation now, so I, which describes the Burgers vectors, is linear, while here, so here it's linear in the exponent. While here it's quadratic in the exponent. So somehow by using this extra expectation with respect to an auxiliary field, we can pass from a quadratic form to a linear form. Now, for any field on the lattice, we use now auxiliary partition functions. So we take our Boltzmann weight, but with this exponential coming from this Fourier argument here, summed over all configurations. So it's a partition sum, but now with this extra auxiliary field phi, depending on the temperature. And here's again a partition sum with this extra factor e to the I sigma I, which was not present in the partition sum before. And we can now write this as an expectation of this partition sum depending on the phi. Then it turns out that the ratio of these two is a Fourier transform of sigma I we had before. Okay, so the next step is a cluster expansion in the polymers. Let me review a little bit the theory of cluster expansion in polymers, which we use here. So let's look at all configurations of Burgers vectors denoted by I's, such that the support is connected and non-empty. So think of this could be such a component. And if we take another one, we say that it's incompatible with it when they overlap. So we say that I and ij are incompatible, and for technical reasons this is denoted by a tilde and not by a crossed out tilde, that I and ij overlap. So you should think of I and I prime being close together. So this is why we use this tilde. They are incompatible. You can't have both at the same time because they overlap.
But excuse me, you are in 3 dimensions, right?
We are in 3 dimensions, of course, yes, but I can draw it only in 2 dimensions. But you
they cannot interconnect, is that what you mean?
I can hardly hear you, unfortunately.
They cannot interconnect, or what do you mean by this overlap in 3 dimensions?
So you mean something like this? So in 3 dimensions, so there's no crossing, but maybe I should draw it like this. So we should use this as a 3-dimensional picture. This is certainly allowed, so they are compatible. Did I answer your question?
Yes, exactly. That was the question.
So they may be twisted, but they should not overlap. So this here is no overlapping. And now let's look at the set of cluster configurations which are compatible. So let's say n cluster configurations that any two of them are compatible, not incompatible. And the weight they get with a given auxiliary field phi is this ki phi is just our Boltzmann weight for the dislocation, and then this part, which when you take the expectation with respect to phi, gives you the elastic part of the energy. And then we do a statistical model, statistical mechanics model with these weights ki phi, which is you take for your configurations up here, the product of all weights of i's in this configuration, sum over all configurations of n entries such that they are mutually compatible. And then you take a generating sequence sum over n equals 0 to infinity 1 over n factorial and the expectation of that. That's a description of the set beta of sigma. Okay, now in order to take the logarithm of the partition sum, it's convenient to use the Ursel functions. Here are how they are defined. So the Ursel function at arguments I1 to IN are the sum 1 over n factorial, the sum over all connected subgraphs of the complete graph in 1 to n. So say you have 1, 2, maybe n is 4, 3, 4, then one such graph could be this one. So it's connected, having for n equals 4. The product over all edges in this graph, here it's 4 edges in this example, and minus the indicator functions that I and ij are incompatible. So for any finite set j tilde, let's assume we have any finite set j tilde. So it's you can think of the j before, but it's more general than this here. Let's assume that we have a reflexive and symmetric incompatibility relation on it, and well, this is a little bit more general than what we did before. Then let me, because I'm running out of time, just go a little bit fast over this part. Then the partition sum in this very general model, this is a standard fact, has a formal power series as its logarithm. So the logarithm of it has a formal power series where the coefficients in there are just these Ursel functions. And here is a criterion, I don't have time to go into the details of it, when this series for the logarithm actually converges. So in this case here, so this series for the logarithm of the partition sum is actually convergent. Okay, well, in order to check this assumption that verifies the convergence of the cluster expansion, we use a Peierls argument. I was explaining too slowly, so I cannot go into this Peierls argument anymore. So we check this assumption of the convergence of the cluster expansion, and at the very end, it allows us to give our Gaussian lower bound I mentioned before. I'm sorry for going so fast over the ideas for the proofs. but if you want, you can look it up in the paper. I apologize for being very fast at the very end. Thank you very much for your attention, and I'm looking forward to questions or comments.
Does this work? Can you hear well this microphone?
I can hear you, but I can not hear you very well.
Yeah.
Maybe if you speak loudly, it could be better.
Do you know which microphone is it? I don't know.
No, it's even worse. I put my ear very close to the loudspeaker of my laptop, but I can hardly hear you.
Okay. So doesn't work, right?
Sometimes I hear you a little bit better. Sometimes I hear you not so well.
Sounds like this is not the mic.
Maybe I try to increase the loudness of my speaker. Could you say something again? Maybe it's better now.
Hello. Now it works? Now it's better?
Now I can at least understand you.
Okay. Okay, thanks. Okay, so are there any questions? I bring you this microphone to anybody who.
What is specifically three-dimensional in your result?
In two dimensions, the theory is much less interesting because in two dimensions, dislocation lines become dislocation points. So as you can see in this picture, you can have localized defects in two dimensions, but with Burgers vectors, you cannot have localized ones in three dimensions. So more or less everything changes and actually becomes simpler in two dimensions because here this whole curl field then is in one dimension lower, which is we have only the first exterior the zeroth derivative rather than the first one, and well, all these constraints with this balance condition, this Kirchhoff rule condition in two dimensions completely gets lost. So in two dimensions, so there's no point about this theory. It only becomes interesting in three dimensions.
So any other questions? It seems like it's not the case. Okay. So, well then, thank you very much. Thanks for the.
Thank you.
Thank you very much, folks.